Oh, yeah, Jeremy. Hello, Jeremy.
Hello.
Hey. Yeah. So here there are two of. I think let me move this. Hopefully, it goes slow. Oh, nice seeing you, Jeremy. Yeah. It's been some time.
Yeah.
You've grown hair. Long hair. So good.
Yeah, it's been an adventure.
So that's Jeremy, Christian, and Wahid are in the classroom. So Jeremy is the one who wanted to.
I'm the one making it all annoying.
No, I think good that you at least asked. Yeah. So let's see. Should we'll try. Yeah, you were a student here, I think, a few years back, correct? I think.
Yeah, it's been like 6 years now.
6 years. Did you have any overlap with Wahid then?
I came in fall of 2014. I don't really. When did you start? When did you start?
I started in 2013, 2014 era, I think, and then went like a year and a half or 2 years. I can't really remember. It's been a while, so.
Seems like you guys had some overlap, but that doesn't mean that it's a big university. Good. It's nice to see you. Yeah.
Yeah, I'm glad to be back. So.
Hopefully all this works out. Notice that I will. I think what I was told is that if everyone agrees, then it should be possible. But then I don't have any control on the occupancy or the enrollment thing. So probably the department chair will be able to do that. We'll see how it goes.
Yeah, I mean, worst case scenario, I've already waited 6 years. Not a huge deal. So.
Okay. Yeah. That's so. Let's wait for a few more minutes. Others might be coming in.
Should be.
Yeah, Bowden usually, two of us, like Christian and Bowden, usually are in the classroom, and others are attend from online. But what he decided he wants to do today, you said you will be here.
Yeah, probably most of it. Probably 9 out of 10 times I'll just do it online.
Yeah. So Christian, were you around here in Carbondale, or did you go home?
No, I went home for Christmas, the holiday. I actually did some traveling. I got a snowboard last year, so yeah, I felt like last semester was kind of rough, and I was having trouble finding motivation, so I kind of wanted to just take a couple of trips. So I went to Colorado and did some snowboarding out there, and then I just got back from a road trip. I went to Ohio and New York and up to Vermont, and then back to Pennsylvania. So something like Boston and Philadelphia, and did snowboarding and stuff. Yeah.
So tell me, what is snowboarding? What?
It's like snow skiing. Have you heard of it?
Yeah.
Except it's like a skateboard flat, so you stand like a skateboard.
I see. I think I've seen it. Yeah. Okay.
Yeah, it's a lot of fun.
Okay, so did you have friends with you? Or?
I had a friend that went with me to Colorado, but then I did the road trip by myself.
Okay. So did you get to do any snowboarding there?
Mm-hmm. Yeah, that's what I planned out because I have, it's called an Epic Pass. So Vail Resorts in Colorado owns a lot of ski resorts through the US. So you can buy a pass and then have access to all of them. So I did that and then just plotted my route around different ski resorts. So I went to like 5 of them in the Northeast.
Pretty cool. Yeah, sounds cool.
Yeah, it was a lot of fun and stayed pretty socially distant from everybody because, you know, on the mountain, you're just snowboarding and everybody has to wear masks. Yeah, but it was a lot of fun. Yeah, I feel a lot more relaxed and refreshed this semester.
Good. Hey, Bowden. Yeah. Yes, Curtis is there. Yeah. So, hello, Curtis.
Hello.
Yeah. I sent you guys an email. I think most of you reply. I'm waiting to hear from two more of you, Travis and Wahid. If that's fine, then I'll go ahead and forward it to the department, and then hopefully the registration should be possible after that. We'll see. Okay. So since okay, I should distribute. Those of you who are, oh, hello, Travis.
Hello.
Yeah. Travis, did you get an email that I sent regarding occupancy?
Oh yeah, I actually just saw it looking for the passcode. Yeah, I'm fine with that. I probably won't be in person most of the time, so I'll just join via the Zoom call.
Would it be possible to just respond to that whenever you get a chance?
Yeah, I'll shoot an email back. So
okay, so those of you are online, do you know how to reach the website for the course? Oh, let me write this down. Works. Where am I? It's a bit confusing. Again. Okay. That's good. Oh. Is it readable? Let's get on that website, and you should be able to click on 420, physics 420. And that should be TC, and how does this go? 2021, so spring semester, SIU physics 420. I think that should be the website for course. So while you guys, and there should be a link for syllabus. That's what, since we are Jeremy, I will very quickly go over the syllabus, but most of you, it's very much the same as last semester. So. I'm also supposed to do attachment. So I handed out the syllabus and the first homework. That's what I did. So the lectures will happen exactly like this. I'll be able to write on the board. Those of you want to come to the class, those of you prefer online, you stay, you can still attend. And if you miss the class, there will be a recording for this, which will be available on YouTube. Again, available. The link for the YouTube playlist is available on this course webpage. And since what I'm expecting is that currently there is an enrollment of 5, we will, if everything works out as I'm hoping, there'll be Jeremy enrolling, and there'll be one more, like we had Matt last semester. He will also probably register. So we'll be 7 of us, and including me, that will be 8. But still, we cannot have more than 5 people in this room. If we decide to have exam, which will require everyone here, then probably we will have to put it in two different classrooms. So something we'll have to arrange for that, or else like Jeremy's that you put on the video and we'll take the exam like that, or make it completely take home. So those are the options, but we will see as it comes. This will be a continuation of what we did last semester. Last semester mostly we did electrostatics. Here, this semester we will do magnetostatics. That is magnetism basically. And that's probably going to be about 4 weeks. 4 to 6 weeks, let's say. Next is we will release the, notice when you use the assumption of statics, electricity and magnetism pretty much decouple, right? Completely decouple. Then we will release that assumption, do dynamics a little bit. So we'll talk about dynamics. So basically where the whole Maxwell equations comes in. So that will be for another 4 weeks, 4 to 6 weeks there. And by dynamics, what do we mean? Notice that electric field and, or let's go back, all of us probably have heard about Einsteinian relativity, where velocity is relative. Right? Whether I am moving or not, it's a relative concept. If I'm at, with respect to myself, I'm at rest all the time. But if someone else is observing me, if you're moving in that direction, you will say I'm moving towards south. If you're moving towards south, then you will assume that, or then you will feel that I'm moving to the north. So that's a very relative concept. And it will work out, it will turn out that electric field and magnetic field also are relative concepts. There is no absolute concept of electric field. What is electric field to one person, in another frame, if you're moving, there will be a magnetic field produced, which is not surprising if you have to actually think of it. So for example, let's say this is a positive charge, right? There is an electric field associated with it. That's electric field, and there is no magnetic field produced by this. And now let us say that your, how should I say, what's the best way to say this? Easy way. Let's see. How I move. Okay, so let's say there is another charge, positive charge, and it is moving with velocity v. Correct. It will of course experience an electric force, which is Q times the electric field. That's standard. We should all, that's a simpler situation. But there is also a magnetic force, which is Q V cross B. Right? So this is a charge Q. So this charge can experience two forces. One is the electric force due to this charge, and one is a magnetic force, but the magnetic force is zero because there is no magnetic field here. Right? So there is no magnetic field, so there is no magnetic force. But this whole thing changes if someone were to move. So according to an observer, let us say this is an observer, let's say that's an observer, and who is moving with a relative velocity vr. If you're at rest, this charge is at rest. But if you're moving, now with respect to this person, this is moving with a velocity vr, and this becomes V plus VR. Very simple terms, even Galilean relativity we are talking about, but we have to use Einsteinian relativity. And the main idea is that the moment this moves, there is a magnetic field produced. So in the new frame, that is actually a magnetic force that will be there. So the main idea is that this electric field that we are seeing is only a frame-dependent quantity, and we have to find out how electric and magnetic fields transform from one frame to the other. Earlier, we have talked about how velocities transform, like v1 plus v2 divided by 1 minus v1 times v2. That's the formula for addition of velocities. Now we have to find out how the electric field transforms if you're in another frame. How it is. So that's what we will do here. And so that will be about 4 weeks. Next is, once we can get a picture of how things move around, we can also talk about what if a charge was accelerating, and that leads to the idea of radiation. So maybe you're already aware, whenever a charge accelerates, it has to radiate. If an electron, for example, if it is going with constant velocity, it turns out we will show that it doesn't radiate, but if it accelerates, then it will radiate. So that is pretty much like it emits photons, and emitting photon is like if you have a if you have a gun and you're shooting a bullet, but also imagine that there will be a back reaction associated with that. So that leads to dissipation. So we'll talk about radiation primarily, and with that, we will also talk about a little bit about scattering. That depends on how much time we have. And overall, so this will also be about 4 weeks. So it's broadly about 12 weeks. We have around 15 weeks of classes. So hopefully this is the primary 3 topics we will cover. As far as textbooks and resources go, you have seen how it goes. Like there is a textbook that is Griffiths, but most of what I do is I go by the topics, and the idea is that when you go back and look into Griffiths, you should, each section of the book should be imagined to be like a problem. Like the homework problems I give is pretty much I take a topic from a textbook or a section, usually old textbooks, and I break it into many 4 or 5 pieces. So how do you test yourself? That's where the textbook comes. You go back and check out a section of a book, and if you're able to follow what is given, and if you're able to connect with the lectures, that should be a little confidence that you're it is going good. Otherwise, you have to go back to the lectures and try to understand what's going on and read more of the textbook. The evaluation and grading, there will be 40% for the homework. And last time we had 3 exams. So this time we will have only 2 exams, 2 midterm exams and a final exam. I think last time the quiz was weighted less. We will have, I think I was thinking that quiz was getting too much, too many questions, but I decided to have it still because at least there was one feedback which said that the quizzes were productive. So I have kept the quizzes, and what I should mention something about the quizzes. It's important, I think. So we will have during a lecture on quizzes. So during a lecture, randomly, I sometimes pose a question. It might not even be a correct question to pose. Question itself could be wrong, but you track as the lecture goes on, what is what is being asked, and you go back home and just look up what it is, what was the question, and give it some thought. It is not expected that you spend in too much time on it, because as I said, the question itself might be wrong, but try to understand what the question was and frame it, and don't spend more than 10 minutes. If you don't have anything to write, at least write the question and say that whatever you found on the internet, you can use any resource you want, and you submit it back on D2L. So submit on D2L. And at the end, this plays an important role. Is that clear? Jeremy, you're the one probably new. Is that clear what I meant by? You're muted, I think.
What do you mean, like new?
The quiz, how it's going to work, like basically during a lecture, there will be randomly, I come up, like usually a discussion leads to that.
It'd be like extra.
Oh, okay, yeah. I watched some of the other videos and kind of followed along with that already. So.
Oh, okay. So here is what happened. I called it extra credit, and I got a feedback saying that you don't call it extra credit because you have points associated with it. So that's why I changed.
Extra points, though.
Yeah, it leads to some
yeah.
contribution, but it's also 10 points is mandatory, right? You see what I mean? You can lose points.
Okay.
So this was especially in the introductory physics course, more than one feedback they said, why call it an extra credit when? So I thought, okay, I'll change it to quiz, but now you say it's not as good. So okay, at least now that I've stuck, I'll stick to this semester. Maybe I'll find a better word next time. So what I mean by quiz is that during the lecture, I randomly come up with a question. Sometimes, if there is no question, you just say that there was no question. If there is a question, you try to interpret the question, whatever I meant there. Go to the internet resource or the textbook anywhere and read up a little bit about it and write a 4-line answer, I think, not more than, don't spend too much time. That's what I'm discouraging you from spending too much time on it. But if you're interested, you should spend time. But for the grade, don't try to spend too much time. I would say 10 minutes. And then you just submit that. The grading will not be for the correctness of the solution. It is more for attempting on that. So my way of assessing is that, yeah, you went back and sincerely looked at what the class was talking about. That's the way to look at it. And it contributes to a curve for the course later on. Did I say that clearly enough?
No. Oh, I don't know if you mentioned it.
Oh, no, about the curve, I haven't mentioned yet, but about the quiz, is that clear what I mean by a quiz?
Yeah.
Yeah, okay. Now, let us say that in the end, you get about 8 out of 10 in the quiz, okay? So that means that that's 0.8. I'll call that 0.8, and let's call that Y. And also, homework, that is, what is this, quiz? This is 30%, I suppose, or 40? 40. This is 10, and there are midterm exams. That's 32 into 15. That's equal to 30, and then there is a final exam, which is 20. Note that homeworks are weighted heavily, and at the end, let us say a particular student gets a total of 70 points. This is out of 100. Right, so that's the status. But then I come back and I say that, oh, okay, I want to curve this. So how do I curve? I change this grade, x becomes x prime. And how I do that is I return back all the points that you lost, right? But then everyone would get 100 in there, right? So if this was the formula I used, everyone gets 100. But instead, I gave only one little bit of the points, and this is where the curve parameter is. So let us say that I decide to give back 20% of whatever you lost. So in this case, this is 30. So 30 divided by 20, so that will be equal to, so this is x plus 30 divided by 20 is 6, correct? So this is 0.20 times 30. But, so that's, you're eligible for 6 points, but that's where the quiz comes back. If you get full points in the quiz, then you get all of the 6 points. But you get only little of it if you were to not do very well in the quiz, and that's where this multiplication by y comes in. So you multiply the 6 into 8, so that's 0.8 times this. So it was possible for you to have, so this was what, 70, right? So this is equal to 70, but now this becomes 4.8, right? It could have been 6, right? So instead it became 4 points. So that's the idea there. Is that clear? Right. Again, the idea I want to stress is that quiz is a very easy way to score there, and it helps you to gain a little bit more points in there. And yeah, it gets probably a little tedious that every lecture, it is due before every lecture. That means almost every 2 days you have to be working on it. But then that shows the sincerity of the student in a sense. So that's my way of looking at it. But from a student's perspective, it might be too much. You're doing 6 subjects and probably it might be a little effort. But that's that's the decision I made. Okay. So try to get the quiz done. Okay. Anything else I think I should mention? You guys think I should mention something else? So what are the things due? So there is a homework 1. At least tentatively it is due on 27th, Wednesday. And there is of course quizzes that is due every lecture. And so let me write that, right? And quizzes will be dated. So this is the first month, so January, and the lecture is 20th, right? This is the date, so 01/20, right? It will be due on January 2022, right? The next lecture it is due on. And we have midterm 1, which is relatively far, and it is February 19. Did I clarify things clearly? Oh, I should mention that for the homework, you're allowed to take help from anyone, any resource, the whole internet, the whole of textbook. Even you can look into each other's solutions. Like if you have friends these days, you guys probably don't meet each other, but you can get together on however you want to meet and look into each other's work. That is allowed. Usually in normal courses, that's considered cheating. But here it is, I'm encouraging that, but write your own stuff. The only expectations I have is that you write your own solution, but then you should be responsible about this in the sense that if you have taken help from the book or the internet or from your friends, then that also means that you have to work harder. When it comes to the exam, it is expected that if it is a no help examination, then it is expected that you should be able to do similar problems. So that's the way to look at it. So homework is more of a place to learn, like you learn it by reading textbooks. Homework you're learning. So that's the idea. Okay. Okay. Any questions? Okay. So maybe do something today. So that's- So Curtis, does it help to zoom into the whiteboard? Like usually I used to keep it farther, but again, there was some comments on
Looks
zooming
pretty
in.
good.
It looks better.
I think I'm fine with it where it is.
Okay, so the other way was zoomed out, that you have more view, but then reading becomes harder, I was told. So I'll try it this way, but if you like it the other way, I can zoom out also. Okay, so we want to do magnetostatics, but let's talk about a charge in a magnetic field to begin with. I'm assuming that all of us have an intuitive feel for what a magnetic field is. We all have taken introductory physics, so magnetic field, you should have a feel for it. So let's talk about a charge in a magnetic field. And let me also say uniform magnetic field. If there's a charge in an electric field, if it's a positive charge, it tends to move in the direction of the electric field. It pulls it in the direction of the electric field. What happens to a charge in a magnetic field? Very broadly speaking,
It goes in a perpendicular direction to the velocity of the charge in the magnetic field.
that's correct. Can you specify a little more? Yeah, that's correct. Perpendicular, and then what happens?
Usually circles.
Then yeah, it will go in perpendicular, but then it keeps going perpendicularly, and eventually it will start going in circles. So very simplistically speaking, if you have a magnetic field and you put in a charge there, and if it is at rest, nothing happens. But if it is moving with a velocity, then it starts going in circles. So let me specify that. So we have, let's say this is a magnetic field coming out of the board. So this represents a magnetic field lines coming out of the board. Right, so let's say this is your X direction, that's your Y direction, and Z is coming out of the board. And these are magnetic field lines or points representing that it is coming out of the board. Usually cross represents going into the board. If you have a positive charge, let's say here at this point, so that's a positive charge. Q, if it is just sitting there, it won't experience any force, because what's the guideline? The force is given by force acting on this charge is equal to Q V cross B. Notice if it is perpendicular to both the velocity and the magnetic field, it is like a torque, like the resultant quantity is perpendicular to that. You use the right hand rule to calculate the torque. And in this case, if it is at rest because velocity is zero, then it is zero. It doesn't move at all. It doesn't experience any force. But if there was a velocity, let's say it is moving in the vertical direction, so that's in the Y direction. And let's say initially, this is an initial velocity, that's V naught. And if you were to use your right hand rule, so that's V cross B, you will experience a force to the right. As Christian pointed out, it will experience a force to the right. So it starts bending, right? So it starts bending here. So at the next instant, it is having a velocity this way. But once the velocity is slightly in that direction, again, it experiences a force. Now the force direction changes. And if you were to follow this up, apparently, this will actually go along a circle. So that's what we are taught, and you can geometrically convince yourself about this. Pretty much like why does a planet going with a velocity, a circular motion, when the velocity is tangential, acceleration is radial, how does the motion happen? That's the same idea, But let's try to derive here that why a circle, maybe it is like sometimes geometrically it is not so convincing. So let's algebraically show this exactly how this is. But the same idea, it is pretty much the same form. So let's do this a little more rigorously if you want, algebraically rigorously. So let's rewrite that equation, or let's specify this a little more precisely, right? So there is an initial condition now. So there is an initial condition when the magnetic field was switched on, it was right at this point. So let's say the initial conditions are, because this is a differential equation, we should be able to solve this differential equation and get the solution as the equation of a circle, right? That's what you should do. So let's say initial conditions are that its position is at time t equal to 0. So this is time t equal to 0. That's the time there. Let's say it is at the origin, right? So this point is really the origin. So this is the x. So that's your x-axis, and that's your y-axis. So it starts from the origin. So that means at time t equal to 0, this is 0i plus 0j plus 0k. And we also have to specify the velocity. The velocity at time t equal to 0 is it's going vertically up. So let's say this is 0i plus v0 in the j direction plus 0 in the k direction. We'll come back and give it a slight velocity in the z direction, and then we will see that it's not really a circle, then it becomes a helix. Like it maintains a circle, but starts moving in the upward direction. But for now, let's keep this simple, and we have to keep the magnetic field. I introduce the magnetic field. Magnetic field is coming out of the board. So let's say B is equal to 0i plus 0j plus b times k. The magnitude is so that specifies the problem. Let's write our F is equal to QV cross B specifically. That's the force is QV cross B. So force is mass times acceleration. So this is mass times acceleration is change in velocity over time. It's QV cross B. Let me rewrite it in a certain form. That's dV by dt is equal to V crossed with Q times D over M. From your introductory level concepts, can you recall what QD over M is? So that's some important parameter typically in magnetism. Let's begin by saying what are the dimensions of QB over M? You can look at this and see.
Going to be something per mass.
Per mass, yes, but overall, what is its dimension here? That's correct. Or mass is surely there. No, because there's a velocity there.
Well, if your left hand side is acceleration, though, right?
Yes, acceleration. But only this I'm saying.
Oh,
this quantity, what is the unit for?
So it's inverse seconds.
Inverse seconds. And what is a quantity related to inverse seconds? Hertz, yes. And something going in a circle, you talk about how often something is going in a circle, right? That's a immediate. So this is a frequency. And what is this called for magnetism? That's a special name for this. This is an angular frequency. Let's call this with a subscript C. Why C?
The cutoff.
No. It's called the cyclotron frequency, if you remember. Right? Rings a bell? No? Or not? So this is cyclotron. If you recall your introductory level, so this is called cyclotron. I think it doesn't have to be capital. Cyclotron frequency. Like cyclotron. What's a cyclotron, by the way?
It's just a magnet that they send particles into, right?
Yeah.
So that they go faster and faster because you have a constant
That's
acceleration.
correct. And why does it go faster and faster?
Because of constant acceleration, because it's moving in a circle.
And why is there a constant acceleration?
Because anything moving in a circle has an acceleration.
Yeah, but when something is going in a circle, you don't increase your speed, right? It goes with constant speed, right?
Oh, do they
good point.
change the? Yeah, it's like how like a generator works, right? They keep changing. The
Exactly. It keeps like every time it crosses half of that, it tries to accelerate that. So that's a good point for the quiz. So this is how a quiz will work. So let's introduce the quiz now, right? So quiz for today is look up cyclotron and just write few sentences about cyclotron. That's all, right? How does it work? How does cyclotron work?
That's the one they use at Fermi Lab, right?
That's correct. That's exactly correct. Except that I think, yeah, one should clarify this. Okay. Yeah, in Fermi Lab, what happens is that you have a magnetic, yeah, pretty much the same, I would guess. Yeah. It's just that I think there you can really accelerate even in a region because, yeah, okay, how about this? Let me explain. So cyclotron has this D-shaped idea, right? And so there's a magnetic field coming out. Let's make it go in. So this magnetic field makes it go in a circle, but every time this crosses here, so there is an electric field also given to this. So what happens is that in between this region, there is an electric field and there it accelerates. So you would say that if that is the case, if this accelerates here, then it will decelerate on that other side. So it's no use, correct? So it accelerates that side and it decelerates here. So that's what you were trying to say. You have to swap this occasionally. So you want to change this to AC. And have the frequency of that AC swapping exactly equal to this, or half of this actually. So that every time it crosses, you have flipped that. So you're accelerating here, then you're accelerating here also. So, and that's a cyclotron. And in Fermi Lab, you can actually make it accelerate at each segment here. Like, because it is so huge, you can actually accelerate at each segment there. And exactly what's the, how do you accelerate? Yeah, let me not say too much. Like I don't know. Yeah, but my point is that you might not say, it might not be completely correct to say Fermi Lab is a cyclotron, but the same idea. It's also going in a circle. Yeah, yeah. Just look up a cyclotron and how does the cyclotron work? And these earlier that those were one of the highest energy particles you could get. But these days, of course, Fermi Lab and CERN is the highest energy particles you can generate. Cyclotron are much smaller. Even in a department, you can have it. Many of the departments have a cyclotron of their own. That's common. But these days, less common, I would say. Yeah. Any questions on that?
That'd be something that you could actually just like order electromagnets and make. Could you put together pretty easily?
Yes, but I think the protection, it starts radiating. So it's more, this itself probably is small. It might be a tabletop thing, but to protect yourself from the radiation, you will need a lead box of 5 meters or something. So usually it is a huge room with a very lead walls, basically. Because the moment the energy becomes high, it starts radiating, and the radiations are too strong after a certain energy. So yes, it is very easy to generate, but very soon your neighbors will start complaining. Yeah. Yeah, good point, actually. Yeah, good point. And I don't know the size either, but usually I've seen that I've seen the walls being thick, but I don't know exactly the size of this cyclotron. Again, that is nothing specific in there. The simplest version of this, when you say that you can design this using electromagnets, what is this called? The mass spectrometer is pretty much a similar concept where there's a magnetic field, charge goes in a circle, you don't accelerate them, that's the only difference. So a mass spectrometer is the same idea. There's a magnetic field, is it visible there? Yes. So there's a magnetic field and there's a beam of charged particles, let's say there are carbon molecules, you have charge them first, and then you make them enter the magnetic field. And based on the charge, that decides the radius of this. So that's the radius R. Yeah, QB over M, the radius of this is decided by this charge Q. And where it comes out, so if it is in this bin, it has certain mass, it is this bin. So based on which bin it arrives in, you know the mass of the atom or the molecule. So that's how a mass spectrometer works. That's the most standard ways of measuring the mass of a particle. Is that clear? Christian, you're bothered?
No.
Yeah. There's a little more specifics here. You give there is an electric field that gives a velocity here. So this depends on the velocity V0 also. So there's a little more specifics there. So that decides where this bin is. But the main idea is that this radius is decided by the charge. By the mass. Mass. And it's inversely proportional to the mass, so that then you can measure that. And the mass spectrometer I've seen is you probably, if you've worked in a lab, how big is the mass spectrometer? I think this big, I guess, right? Meter by meter, meter by meter by meter size. That's typically the size. Okay, so we have our equations of motion. 5 more minutes. To be dV by dt is equal to V crossed with omega c, where, so this was a magnitude I said, because typically when we study a steady cyclotron frequency is a scalar, so you don't associate a vector with it, but B is a vector, so let me define a vector. Call this. It's a magnitude of that quantity that is the cyclotron frequency, but give it the direction of the magnetic field, so that gives you an axis associated with that. So it's about, usually whenever there is a rotation, there is an axis, a related acceleration axis associated with that. The direction of omega c is the axis about which the frequency is measured. So our equation of motion for this problem is acceleration is velocity crossed with the vector. Right. Not the velocity dependent force. Right? Where else do you see a velocity dependent force?
Could you repeat the question?
Where else? Give an example of a force that is dependent on the velocity. What I mean.
With the drag force?
Yes, very good. Yeah, drag force is a velocity dependent force. But that's typically a drag force is proportional to velocity if it is going slowly. If something is going relatively slowly, then it is proportional to velocity, or negatively proportional to velocity. If you're going faster, for example, if you're skydiving, then it is v squared, it turns out. And remarkably, back right when Newton was working on this, he proposed that will be velocity squared, and measurement wise, it is pretty much velocity square, but it's still empirical. It is not a fundamental law, but when it comes to slowly moving quantities, the drag forces are linearly proportional to velocity. And that has a fundamental feature to that. That was what was studied by Stokes. But it is still empirical. So, but this is fundamental in the sense that is true, exactly true, like that is V cross V. And it is not just linear, there is this cross product relation in there, right? So there is more richness in here. So it's a perpendicular force in that sense. And let's try to solve it. I'll just build it up and then we'll solve it next class. Any questions or comments associated with that? Okay. So let's let me quickly zoom in. Okay, so let me just build this up and then we will leave it for next time. This is in the z direction because that's the direction of the magnetic field. V cross see what it is. Let's do it the standard way, right? We write it as a determinant. So that's I, J, K. So this is Vx. This is what we want to solve for. First, we will solve for V, X, Vy, Vz, and then we will solve for X, Y. So that's 0, 0, B. So that's here. So that's equal to I component is Vy times, oh, this is omega C, sorry. So I changed magnetic field, but now I've scaled it with respect to, so that's omega C in the I direction. And J is, this is minus, right? Vx omega C in the J direction plus 0 in the K direction. So we learned that dvx over dt, that's an acceleration in the x direction, plus dvy plus dvz over dt in the k direction. That's the left-hand side of our equation. That's equal to vy omega c in the I direction, omega c in the j direction, plus 0 in the k direction. Equate the three components, we get the velocity in the x direction.
Professor,
Yes.
sorry to interrupt. Could you scroll the camera up just a little bit more so I could see the...
Oh, I moved it too far. I think I was hurrying up.
You're okay. Thank you very much. I appreciate it.
Good. So that's your equation in the I direction. That's the equation in the y direction. Notice that x component of velocity is coupled to the y component, right? That's what happens in a circle. When something is going in a circle, the coupled equation, and this is equal to 0. And of course, the idea is that once you have this coupling, substitute one into the other, right? Vx can be solved for here, and you put it in there. Then you get a second order differential equation, and then we will try to solve that. We'll come back and solve that properly next time. And first, this is only magnetic field, and now we will introduce an electric field also. Like next time, we will also introduce an electric field and talk about those things. So first week, we will do this one. So I'll stop here for now, and we'll come back to this next time. Thank you. Jeremy, how did it go?
Pretty good. I think I
Okay.
can keep up.
Yeah, okay. Good. See you. Hopefully all of this works out. Yeah. Okay.
Yeah, thank you.
Bye-bye.
Bye.